So I'm going to go through question M. So this is the one where you and your friend are taking an exam. You have different answers for some questions and the same answers for some. And you know how many that they got right. You want to know the maximum possible amount that you could have gotten right based on the differences. And so that's where the first observation comes from, is that we don't really care which questions they got right. We don't care which questions they got right and wrong per se. We care about where the differences are between you and them. So like, if your friend got 2 questions right, and this is your friend 1, and they got 2 correct, then they have room for 2 more improvements. And you've also made 2 different answers than your friend. So it's hypothetically possible that these are the 2 that you got correct, and that those 2 can be improved. So at best, you got 4 correct. And most situations take this form. But there is one situation to be particularly concerned about, which is when your friend gets 3 correct. In that case, no matter how you choose which 3 were correct, and one of the ones that you got correct, you would have gotten the opposite answer, and that's wrong. So let's say in the best case, you fixed one of his mistakes. But in another case, actually, is that at all legible? Oh, that is very small. Okay, all right, there we go. So you corrected one of his mistakes, but he had to have made one correct that you got wrong. So this is the -1. And so the best you could have gotten is also 3 correct. Did anyone get the answer and want to explain their approach to their solution? Okay. So the way I did it is I first broke it down into any time that we got the same answer as our friend, we don't really care. We're going to bunch them all together and count that as a number. So we got 2 same answers. And we have 2 cases where we gave a different answer. And these are key. These are where we have the option to do better than them or to do worse. And then finally we have this number k equals number of correct that our friend got. Also worth noting is n equals total. In this way, I've broken the problem down into purely a mathematical one. Because we don't care which exact questions it was right and wrong. We care about the numbers. Because we want to make as many of his incorrect answers into correct ones. The way I visualize this is, let's say these are all the questions. And let's say this is the number of same answers.
Recording in progress.
And this is the number of different answers. The room for improvement that our friend has is n minus k. That's how many that we got wrong. And we're going to try and fill diff with those answers. So imagine it. We just keep these all the same, and then where he got questions wrong, we say that those are the ones that we're going to guess that we got correct. And so we end up getting same plus n minus k. Except when it goes too far and it goes over. Like that. In that case, this part juts out the other side and starts cutting into the parts that we get the same. So you must have gotten some of these incorrect as well. And the formula finally turns out to be, or at least this is the way that I wrote it. So where can you guys see? Able to see up to here. Okay, so I'll write it here. So what this looks like is
They can. Read the box. Read the box.
wait, actually, K is the number.
Unmuted.
Yeah. Okay, I did this the other way around. Yeah, this is what I did. So this is the room for improvement. And then every time we got a different answer, that could be correcting one of the incorrect answers. But if we've got too many differences and it goes off the end, then we have to change some of the correct answers into the incorrect one. And this gives us a decreased number. So if K, which is the number that was originally correct, this step of n minus kind of like does this correcting effect. Oh boy, this is hard to explain. Anyone else have a intuitive explanation?
I have different formula.
Okay.
We use a similar idea for yours. So, starting from this, looking at this, there are two ways that you get a correct answer. So, way one is they got it correct and you got the same answer. So, do you have names or is it?
Friend and you.
So, way one is I can't. That's okay. Your friend got it correct and you agree with them. So you get the same answer as them.
Yes.
And way two is friend got it wrong and you disagree with them.
Yeah.
Let's count these two things separately. What's the maximum number of answers that your friend got correct and that you can agree? Well, that's going to be the smallest. So 1 is going to be the minimum of the number your friend got correct. So friend correct, we've got some other name, but I won't call it that. The minimum of this value and the number that you agree on. Because in the best case, you get as many of the answers that your friend got correct, you agree with them to line up. And how many can line up? Whatever's smaller out of those two values. That equates to like whatever one's bigger gets cut off.
Yes.
And number two, use a similar formula. What's how many of type 2? Well, it's the smallest out of number your friend got wrong, n minus the number your friend got correct. and the number that you agree on, which is n minus disagree on, it's n minus agree. So if you add these two quantities together, that's another way to get the solution.
Yeah.
And I prove this is equivalent to Lake's formula.
Yeah, okay. This is the visualization that I wanted.
Yeah, but not this is simple as your solution or not.
Yours expression is simpler. We're expressing the same concept.
Yeah.
This is the visualization. I thought about it differently when looking at the question, but this I think is the better form.
You're adding like the smallest of these two and the smallest of these two. Or you're adding the whole thing and subtracting the middle part.
Yes.
Yes.
So, okay. This goes both possibilities.
Yeah, hand it over to you now.
Yeah, okay. Thank you, Angus. So yeah, in this situation, yeah, we take the green and green, but we don't get the red. And even if the things are reversed, and let's say the boundary is, it's hard to draw here, but if you have another situation where the boundaries are like this, and like this, if you get the same answer and correct and incorrect, that also won't get you marks. You only want the green region on either side. Any questions? I'll also read chat in case anyone online has questions. Does this make sense? I see where my confusion came from earlier. It's because there is a symmetry between correctness and whether you get the same answer. You can look at the question either way and it'll turn out the same. Okay, there's a question. What problems? We've only covered M so far. Any more question requests from in-person or online? Oh, M. Oh, are you requesting N? I see. Okay. Sure. So are people fine for me to rub out this part? Yep, cool. So the full solution to question N requires an advanced data structure. So I won't go into the details of that in this review because it's mainly focused at beginners. But I'll cover the gist of the solution and the approach. So this is the situation given in sample case 1. So I have the way that I think about the problem, and I'm not sure if it's the best way to explain it. It's about reorienting a space dimension into time. But okay, no, I'll explain the idea though. We can do a sweep line going from the top to the bottom and update as we go along. So we start at the top and see at the beginning, there are no black squares. then once we get down to here, there are black squares. And here, it changes again. And the number of black squares kind of along this row has decreased. And instead of like counting them, we can jump from here to here to here to here. So even though the size of these squares is up to 10 to the 9, up to 1 billion, the number of times we need to change our count is bounded by the number of rectangles we have here. The number of, every time we start or end a rectangle is when that count changes. So our approach is going to be about having a count, maintaining how many squares there are in a certain row, figuring out where the next point is, jumping to it, and multiplying it by its depth. So four black squares, and the height is 1. Here, there's 1 square here and 1 square here. But the height of this, I believe that's 2 colors. I'm just reading this off the sample case in problem N. Oh, I should have re-explained the problem to people who haven't read it yet. You have a bunch of overlapping rectangles, and wherever 2 rectangles overlap once, they cancel out. But if you draw in another rectangle, like this, that would invert this. So this will become black, this will become white, and this will become black again. So these overlapping rectangles all cancel each other out. Oh, well, not cancel, but they invert each other over and over again. Okay. And not to belabor the point, you'll jump again here, seeing the depth is 1, and the number of squares is 4. Now, you can use this to build an O of n squared solution to this. What's the memory limit? I believe it should be 256 megabytes, 1 gigabyte. Okay. 1 gigabyte, does that use, no. Yes, a gigabyte won't let you store a billion integers because an integer is 4 bytes or 8 bytes if you're in a 64-bit machine. So you can't store a billion. You have to like only store, like, in practice, up to the size of the input, maybe a little bit more than that, maybe log times extra at most. But you can't go all the way up to a billion, which is the maximum values that you can get in the input. So we can, okay. So if we wanted to do an O of n squared approach to calculating this, well, okay, we can start with one approach, which is having a binary array, 0, 0, 0, 0, 0, which indicates that every square is white. And then when we start a square, we flip the squares associated with them, 1, 1, 1, 1, 1. And then when the next square appears, we flip those back again, 0, 0, 1. But the problem with this is 1, the size of the array has to be a billion, and 2, it's very slow to update it every single time. But note that it's possible. So that, okay, so based on the approach that we've done so far, if we look at the time complexity we've got so far, the number of steps you have to go down is O of n, as in the number of boundaries is 2n, one to start each rectangle, one to end each rectangle. And the length of it is going to be up to 1 billion. So I'm just going to denote this as max value. But if we can compress this down to O of n, then we have a much more reasonable solution that doesn't use billions and will fit in space. And I'll briefly go over this, and then I'll say that the rest of it, you need to use a segment tree to implement. So to get it down to a length of n, you note that like with the vertical situation, we have start and ends of rectangles. In the horizontal case, we also have starts and ends. And we don't really need to consider the space in between. So I'll have an array of all of the indexes where there's actually something interesting going on. So I might say that this is index 0. Actually, I'll look at the numbers given. Yes, it uses 0. 1, 3, and 4. And I'll keep them as the indices of a rectangle to build. So instead of building this massive one, not indices per se, I'll say because there are only 4 distinct points, we'll only have an array of size 4. And they'll be indicated by 0, 1. And each of them is going to count whether the points between it and the previous important point are black or white. So in this case, 0 to 1 starts off, everything starts off. After the first step, between 0 and 1 is black now. Between 1 and 3 and 3 and 4 are also black. So these all become 1. And we can quickly calculate the sum, the total number of black squares, by multiplying 1 by the distance between them. 1 by the distance between them. 1 by the distance between them. So the total of this is 4. Length 1, length 2, and length 1. Then when we update this again, and we remove this part, we just need to change this to 0. And then we can recalculate. And so now this is O of n, instead of being the total length of the array. Now, all the updates will take the form of, take this segment of our array that we've built, and flip all the values of it inside of it. And that sort of operation is very well suited to segment trees. And I'm not going to go over the details of them, but I'll post you guys a link to a very similar problem online. Whoops. Actually, no. Okay. This article will help it. We'll give you a very similar example. Technical difficulties. Give me a minute. Okay. And this will go over in more detail. Do people have any questions? So basically this O of n step of updating all the values is going to be improved to log n using a segment tree. I'll briefly explain what a segment tree is. It's a data structure that you build over the top of the array that stores metadata about it, about segments of the array. And instead of working on the underlying array, you work on this data structure and you query this data structure, and that's much faster. You can read about it. I posted in the Zoom. Any way to get it to you guys?
Oh,
Yes.
we have search terms.
Oh yeah, okay. Yeah, okay. You can search for segment tree. Plus sweep. That's relevant. Sweep line. Okay. Where's the article? The article, oh, the specific article is on top corner.
You can also search range queries with like more
Okay.
search.
Yeah, it's meant like you can put up the specific enough search terms that anyone second for that you can search it up.
I see what you're saying.
That's probably more efficient.
Yeah. So you can search these terms to find them online. Cool. Yeah. So any questions? Any concerns? The first two steps to get down to O of n times n, I hope I've explained that well. That does not require a segment tree to understand. So if there's any questions about up to here, go ahead. Online as well. Right? It seems like everyone's very happy or very scared, either or. Any more question requests? Oh, actually, yeah, each. Okay, well, online asks for D. E2, okay, yeah. E has gotten 2 votes then. Sure thing. I think E is a pretty fun question. Okay. I'm gonna need another booklet. This one's just missing question entirely. It's pretty funny. Okay, I got another booklet. This one has question E in it. Oh, A is so hard. Oh. Yeah, the thing is I found A hard, difficult, like hard as well. I don't know if I can really help with you there. All right. But problem E I can do. I'm gonna put these up. Okay. The cool idea here, though, is the number of possible states to consider. Give me a moment. So it says that the digits 1 to 9 are written down. So you have all the states of different ways that digits can be written down, 1 to 9, and each digit is either there or not there. The binary choice. So the total number of states is like 2 to the power of n. And 2 to the power of 9, sorry. 9 being the 9 binary choices we have. So with only 500, so 2 to the 9 is 512. So with only 512 states, you can do a lot of different algorithms with it. In particular, n squared algorithms become quite easy. I believe you can do this faster than n squared, but I'm not going to go over the details of how to optimize the speed because it isn't super critical in this problem. But of course, if your algorithm is running in cube time or higher, then you should be concerned. But the cool idea, let me just double check what I wrote. Yeah. Yeah, the cool idea is a pretty straightforward kind of try everything. So the first thing I did was I didn't pay attention to the specific input. I kind of solved every single case and then went back, actually read in the input and calculated for that input what to do. One implementation detail, which can make life easy for you if you haven't seen it before, if I have the numbers 1, 2, 4, and 5 available, then first I'll list out all of the options. Assign each one a binary number. So I've assigned a binary number to each one. You may observe that they don't quite line up. So like 2 to the 6 is 64, but I've given it the number 32. It's because the way we label it doesn't actually matter. What matters is that any combination is going to have digits, is going to have the numbers like this: 1, 2, 8, and 16. And I can add them all together and get a unique number that represents this state.
Write out of binaries in these things.
Yeah, that's a good idea. 1, 1, 0. So in binary, this is what the numbers look like. And so this situation looks like 1 plus 1, 0 plus . Yep. Yeah, to write it in binary will be, okay, I'll rearrange it so that it's easier to write in binary. We label which ones we have in our state, and the rest are all 0. And this is our binary number. So to be clear, digits, number. This combination represents this binary number. This is an implementation detail that can make it easier to track states. You can do stuff like, if you want to check if it's possible to go from state A to state B, what that means is that the digits in state B all exist within A. So let's say I roll the dice and I get 6, so I can remove 6 worth of dice. I might want to consider the state like this, where I've removed 4 and 2. I can easily check that this is an element of this, like it's same state, because if I do bitwise AND, between them, I'll get the same answer here. So A and B equals B. This indicates that all the binary digits that are here are also in the original number, because none of them have been deleted by the AND. None of them are missing. That's an implementation detail. Okay, I probably should explain the bulk of the solution first, though. I'm going to track. I'm going to assume the game is to get the minimum score, because getting the maximum score is the same thing, but kind of like just side change it out, like the functions and stuff. So I had a function evaluate. That says, if you're at a specific state and you roll dice and you cannot take any dice or take any of your numbers away at that point, what's the score that you have? And it takes in a state, which is a number, and will give me that score. So let's say I'm in this situation. And with my dice, I roll, actually everything is possible with that, I think. 6, 6. Yeah, so not a great example, but let's say if I evaluate the states. Yeah, I think I'm making this more complicated than it needs to be. But yeah, evaluate 5, 4, and 2. So let's say I roll the 12 with my dice and I'm unable to take digits away. Then this will return the number 245, which represents the score that you would get if you stop the game there. Then, for every state, I go through all 512 of them. I calculate all the dice rolls that could occur. I look at all the possible numbers that you could take away as a result of those dice rolls. Counted how many are there. If there are 0 possible numbers that you could take away, I have this value. And if there are options, then I take the minimum. I take the one that has the lowest score. And then from that, I do a calculation. So a 1 in 36 chance of rolling a 1. Yeah, of rolling a 1. A 2 in 36 chance of rolling a 2. A 3 in 36 chance of rolling a 3. And for each of these, I try every possibility, a possible combination of numbers I can remove, and see what scores they give me, and pick the one that gives me the lowest score. Yeah?
What do you mean by the evaluate function?
The evaluate function, or doing this whole process on that number. So, okay, some people did this recursively. I did it iteratively. It might be easier to explain recursively.
So you use the evaluate function if you can't remove anything. If you can, then you basically think
Do a recursive thing, yeah.
get scores from the
Yes. Maybe I can call this raw evaluate. Or final. I'll call this final evaluate. So if you end here, then it would be this process. This is the scoring that they describe in the problem, of just listing out the digits, and that's your score. But the intermediate evaluations will do this kind of weighted average of all the other options. And if they can go further, then weighted average further and further down.
That's just how probability is.
Yeah, expected value.
You did an error. What order do you work with?
Yes. So Odin asked the question. I did this, the fact that I did it iteratively, not recursively. What order do I visit the states so that I can actually evaluate everything, that I've already calculated everything that I need to? That's one of the details. That's one of the good things about enumerating like this. I go in numerical order. There's 500 and the states 0 to 511. And I literally go in that order, and I'm guaranteed that I've visited all the previous states. Now, how can I show this? If I have some state like this, the only possible next steps is to remove a digit, to remove one of these bits. And in doing so, I have a smaller number. So every path that I could do to progress the game will give me a smaller number state. So if I've already visited all the smaller number states before it, then I'm guaranteed to evaluate it. So I have general evaluations required to do it. I feel like I might have left stuff off in a way that some people wouldn't understand. Do people want me to try and explain this further, or would you like me to move on to a different question?
More about the
probability part?
Yeah.
Yep, okay. I'm getting some requests to explain this further. Very well. I will in fact share my code. Oh, I may not share my code. It's pretty messy. It still has like commented out French functions.
Do they want you to just explain the story or they don't understand the final part either?
So one request for the probability part, and okay. I'll give a concrete example, and that way it'll be better. I'll do it over here. Sure thing. Oh no, my battery. Oh no, yes.
I got my computer. Do you not have a copy?
I have a charger, but it's not going to reach.
There's tablet from the.
Oh yeah, right. I did not see that. More technical difficulties. All right. Okay. I'm going to use pretty small numbers. So yeah, let's suppose I'm in the state with the digits 1, 3, and 4 are the numbers that I have remaining. All the possible rolls that I could do, I could roll it. So it's 2 dice that you roll together. So I could end up rolling a 2, a 3, a 4, a 5, a 6, 7, 8. That's going to go for what, isn't it? I can tilt. 9, 10, 11, or 12. These are all the possibilities that I could end up rolling. If I roll a 2, there's nothing I can do. And my score is equal to the eval function. 1, 3, 4. Does this make sense to people? 2, there's no combination of digits that I can take away. If I roll a 3, then I can take this away. So it becomes run this function on 1 and 4. I am not going to do that yet. But I'm going to call this function def score. 1, 2, 4. I'm going to say that I call it recursively at this point. So to calculate this, to calculate the score of these states where we have 1, 3, and 4 as digits remaining, we have to recursively call the state where 1 and 4 are the only digits remaining. If we have roll a 4, then we can remove either the 4 or the 1 and the 3. So we're going to score both of them. And see which one has the minimum value. Is that legible online? Can you guys see my board? Or would this is going to be a bit difficult otherwise. It is visible. Cool. 5, there's only one option. So, but we again have to recursively call. And score 3. 6 has no options. So we default to this. 7 has an option. Score 1. 8 has one option. But we know that that is equal to 0. We can still do the recursive function call and let the function tell us that it is equal to 0. 9 has no possible options. 10, no possible options. So on and so forth. We can calculate all of these steps and then return, okay, we have all the possibilities, let's aggregate them. But not every outcome is equally likely. If you've ever played a board game with 2 dice, 2 and 12 are very rare occurrences. And you tend to get numbers in the center more. The concrete probabilities this is so you can calculate the concrete probabilities using a table. Die 1 and die 2. I'm not going to fill in the entire table, but I will note that this is 2, this is 12, and you have this diagonal of 7s through the middle. And you can isolate them into bands. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you'll have diagonal bands, but they're all the same number, and they're increasing in size. So you only have one option where it'll roll to 2, 2 options where it'll roll to 3, 3 options where it'll roll to 4, so on and so forth, until you get to 7, which is 6 options, and then it decreases again each time. So there's only 2 options to roll 11, a 5 and 6, or a 6 and a 5. So I can put this into a weighted sum of all of these values. So 2 appears 1 time, relatively appears 1 time, 3 appears 2 times, 4 appears 3 times, so forth. I'm actually going to write them at the top because otherwise it's going to be harder to follow. And then after we get to 7, it decreases. So we get whatever score was here, we multiply it up. And then our total, we divide by 36. Can you see it that far? You can. Whatever total we get after adding them all together, we divide them by 36. This is taking a weighted average.
Because each die has 6 possibilities and your key die has 6 possibilities.
Yeah, exactly. There are 36 possibilities. Another way of describing this is this has a 1 in 36 chance. This is a 2 in 36 chance, so on and so forth. But instead of putting those values in here, I've factored it out and done it at the very end. But it's equivalent. But yeah, so here's a weighted average. And this idea comes from probability and saying, okay, these are the chances of each of these outcomes happening. And we don't know what's going to happen, so we take the expected value. And that's our average score. Okay. Does this make more sense now? Does anyone want me to explain any detail of this further? Ooh, seems people are good with this question. Okay, any more question requests then? Oh yes, that is overdue. Okay, so I didn't really take a look at D in the contest because it looks extremely painful. And from what people have been saying, they mostly agree. But I do know the concepts and the idea on how to solve it. So I'm going to rub this part out. So the overview of the question, the overview of the solution is you BFS to find the answer. So the way to visualize this is that each time you do an operation, you're transforming the string in some way. And if you can move to another string in a single operation, then those two strings are adjacent, or at least there's a directed arrow going from the first string to the second one. So in this question, in the sample case, these are given as the first two steps that you do in your process. Okay, well, to explain to people who haven't read the question, you have a string and you can use the letters of the string to do operations on the entire string. And so it'll do some transformation there and it'll turn into a new string. So you repeatedly do these transformations to get to a new string. Now our task is we have a target string and we need to specifically click the buttons to transfer us to the right location. Now, the right location being the final string that we want. In this question, there are 8 buttons, 8 letters that we can press. There's a lot of complexity in what each of the buttons do, but ultimately it will transform the string in some way. So there are 8 outgoing arrows from this string, and every string will have 8 outgoing arrows like this. And you can imagine this and imagine all of the different strings and how they all connect to each other, and it becomes this enormous graph. And the task then becomes searching through this graph for a path from your starting string to your final string. In the first sample case, that's a string of 8 beads. And how do you search for the shortest path through a graph? BFS. So the underlying concept is BFS, and all the details around it are a matter of implementation, about matching the constraints of the problem, kind of like representing this situation in code. Any questions about this? Seems like people are happy. Anyone online have any questions? Sorry, I don't have a whole lot to talk about this. Okay, it seems like people are happy. Any more question requests then? Question I. Oh, actually, that was already requested. Cool. Yeah, I will go over I. All right. Cool. I'm going to rub this one off. I'm going to put up like a snippet of the case given in the question. So I'm going to ignore the rest of it because I don't want to write it all on the board. Some things to note. So these are the 2 tiles. So the problem, for those who haven't read it, you basically want to identify the tiles where all the neighbors are larger than. Now, in theory, this is quite straightforward. You go to each one and you then check each of them and compare against it and see if it's larger. There is a little bit of difficulty to this problem in implementation. It can get a bit finicky. Okay, I will share some code then. Okay, wait, actually, first of all, I want to know, Raj, what do you want to know about question I? What is your difficulty that you're having?
To be honest, I'm not too sure because the code was working just fine on our side. I tried a bunch of different cases, even with larger numbers. But then when we submitted it, it always came back with wrong answer.
I see. Okay, paste your code in and we can try debugging it.
Yeah.
I might come back to it based on if other people have questions, because debugging can be quite boring.
Yep.
But it seems like a very implementation specific detail.
Just grabbing it now.
Does anyone else have a question request? And does anyone else want me to explain I further? Okay. One for F. Yeah. Is Angus around? Yeah, Angus here. Angus knows how to solve this. Yeah. I don't know how to solve this problem. Yeah, other problems first. Yeah, you guys have to be patient, I suppose. But this is a complicated. Yeah. Yeah. In a previous contest where I saw this problem, they did explain the solution, but I didn't want to hear it because I didn't want to get spoiled. I wanted to solve it myself later. I also just never went back to solve it. So it is what it is. Okay, F has been requested. Has anything else been requested? Because we'd like to go over anything before F. Oh, okay. Yep, it seems legit. Okay, no other requests. Okay, so I'll let Angus do F, and then, okay, similar problem with L. Yeah, okay. I'll let Angus do F, and then I'll try helping people debug the problems that they were having. Yeah.
Similar idea, just to some of the complexity into the state further account. Yeah, I'll give the one I'm more familiar with. So the first part of this is removing the geometry from it. I'm not going to cover the geometry details. You can ask about them at the end. Yeah, we can talk about them at the end if you want, but it's just line intersection. The short answer is play around on paper. But the idea is we initially get given these weird shapes. And we want to look at in what ways can they actually intersect. And let me reframe the question first of all. So the question says you're given a bunch of wires. Each wire is defined as like a broken line or like a bunch of line segments that starts on the line y equals 0, and it ends on the line y equals 0, and is otherwise always above the line. Additionally, you're guaranteed that it stays within this boundary here. So it never extends past its endpoint. You're given a bunch of these wires that may or may not intersect. You give another wire like this, and another one like this, and another one like this. And you want to pick some subset of these wires However, out of the set you choose, each one you pick must intersect with exactly one other wire in your chosen set. So you can't pick all 4 wires I've drawn here, because, for example, if you pick all 4, this green one will intersect with 2 other wires. So in this example, the maximum we can pick is 2. We can pick, for example, these 2 wires. Then everyone we pick intersects with exactly one other wire. If I also added one more wire here, then we could select 4 wires total. And we could select these 2 and these 2 wires here. Additionally, each wire has a score, and you want to pick a subset with maximum score. Okay, so the first detail is let's abstract away the geometry and look at the different ways wires can intersect. First of all, if one wire ends before the other wire starts, so you have one wire like this, another wire like this, then they can't intersect. So, they never intersect. Second case is, what if their endpoints occur one after another? So if one of them starts, the other one starts, one of them ends, then the other one ends. So they're like ranges overlap. Then they're guaranteed to intersect somewhere. The only, I guess, difficult case is when one of them is contained in the other one. Because if one of the wires is contained within the other one, then you have 2 options. One option is like this, where they don't intersect. The other option is like this, where they do intersect. So for each pair of wires, you first check that if they line in this case, you check whether they intersect. To do that, you can just compare every pair of lines within the 2 different segments and check whether those line segments intersect. So we're going to do that. Google line segment intersection algorithm, and you'll find better tutorials online than I can do. But now let's say we know for every pair of wires whether they overlap. We just computed that, and we have that stored in an array somewhere, which we can do in n squared or something. N squared times 9 squared. Okay. The next step is we're going to compress our coordinates. We're told conveniently that every coordinate is unique. That means the coordinates on the y-axis are all unique. And if we have y-coordinates like y-coordinate 1, and this goes all the way to y-coordinate 8, we have a second wire that goes from y-coordinate 3 to 5 like this. We're just going to renumber all of the x-coordinates. We're going to renumber all the x-coordinates so they start at 1. Make our life a bit easier. So we have consecutive x-coordinates. This means that our x-coordinates, instead of going from 1 to 100,000, now go from 1 to 2 times n. This just, which is at most 300. So we're doing what's called coordinate compression, where we just renumber all of the coordinates along this y equals 0 line, so that we have the numbers in increasing order like this. That makes our life a bit easier. Now let's go on to actually solving the problem. Let's say we select some pair of wires. Like we select, I'm going to remove these coordinates now. We select 2 wires to include in our set. We're going to include these 2 wires here. Then any other wires we include in our set can't intersect with either of these 2. Yep. So any other wires we select must be entirely contained inside one of these regions here. This region on this side and this region on this side. We can simplify these 2 regions a bit by noting that regions are bounded by their x-coordinates. So we can say actually this region here, this region here, this region here, and these 2 regions on each side. If we pick these 2 wires, any other pair of wires we have must be both contained, like every other pair we pick, we're going to pick them pairs at a time. Every other pair must be contained exactly within one of these regions. Because if we picked another pair of wires where one was in here, one was in here, then they'll intersect with this y here, for example. So if we pick one pair of wires, this limits all future pairs of wires to be contained within one of these regions. Yep.
I can't go with one. What do you think?
It can. So let's say that we pick wires from biggest to smallest. So we can pick wires that go over the top. That's a good point. So we're now going to assume the order to pick wires in is such that we never pick a bigger wire after picking a smaller wire or something. That's a good point.
Bigger than the one.
Goes over the top. Like we're going to pick wires in order such that we never pick wires that go over the top of this. We're going to pick that wire first. Right. That's a good point that I omitted. But yes, the wire can go over the top, but we're going to assume that if we want to pick wires like this in the future, we're going to assume that we pick this wire first and then pick this one later. Good point. So we're going to pick our wires one pair at a time, and we're going to pick them such that we pick the outer ones before the inner ones to avoid that case. And so after picking a pair of wires, any other future pairs we pick must be in one of these green regions. Does this make sense now, Odin, after I clear that up? Okay. So a nice approach would be to use dynamic programming. So we could represent a state as a green region and do some DP based on that. To do this, we need a way to accurately sort of encode these green regions. And how can we encode these green regions? Well, they're bounded by some minimum x coordinate and some maximum x coordinate, like this. That's one way, and also you somehow bound the top of them as well. But the one observation is each green region is defined by at most 2 wires, such that it's between two x coordinates and other bounded by these 2 wires. So we can say that a green region, is defined by its minimum x coordinate, its maximum x coordinate, and the up to 2 wires that form a roof over it. And why does this work? Let's say we were to go into this region which has these 2 wires of the roof, and we were to later select some other pair in here, like this. Then this region is defined by these 2 here, this region by these 2, this region by these 2, and this last region here, well, its 2 bounding wires remain these 2 wires here, and this region here, its 2 upper wires remain as these 2 upper wires. And the second case we need to consider is if our intersection looks something like this. And in the same way, for every green region, we can select 2 wires that bound the top of it, up to 2 wires, and the minimum and maximum x coordinate as well. So we can represent one of these green regions, or a region where all our pairs must be within, using 4 values, each of which is up to n. Does this make sense? So we have currently a n to the 4 state. We're going to improve this later, but we have an n to the 4 state for now. So we have a state which says we are within this green region defined by these 2 x coordinates and these up to 2 upper wires. What can we do? Well, we just want to pick every pair of wires, so try literally every n squared pair of wires and check, are they all contained within this green region? How do we check that? Well, we check that for any other wire, we check that its x coordinate lies between these 2 x coordinates, and we check that it doesn't intersect with either of the roof wires. Because for any other wire, if its x coordinates both lie within the range of x coordinates and it doesn't intersect with either of the roofs, then it must be entirely within the green region. And we just try every pair of such wires that themselves intersect. So we're going to try literally every pair of wires that are within the green region that are valid. And we're going to say what happens if we include them in our answer. And what we get is, we get the sum of their corresponding scores plus the recursive value for solving the problem in each of these green regions here. Like the corresponding regions formed that we could place future wires. So what we look like is we have a state, which is our allowed region. And then we try every pair of wires, every intersecting pair of wires. In the region. And we find what's the maximum score if we include those wires? Well, it's the sum of their scores plus recursively solving the problem on each of these subregions. And if we do that, then we get a DP that has order n to the 4 states and order n squared recurrent, so n squared work at each state, which gives us order n to the 6 solution. I understand in general dynamic programming, this is probably going to be too hard. I don't think I have the time to explain what dynamic programming is. So apologies if you don't know what dynamic programming is. But the idea is we're solving on a recursive subproblem. But for people who want to hear the solution, are there any questions about the n to the 6 solution for now? Or are people following along? We've done most of the work. Yeah, we're almost done. The problem is, n to the 6 is too slow. You want the chat in case anyone's asking me questions.
Yeah, there is one comment. No need to encode, use map vector intent to store everything and it works.
I mean, sure. Yeah, if you want. That's up to you. That's implementation detail, right? But yes, that point was that you don't need to compress these, you can use a map instead. And we can for an extra log factor if you want to do that. Yeah, sure. Yeah.
Can we just when we like find out that like the wires that is connected to each other, so like can we change the problem if we just graph problems like there are 300 vertices and that still wants like 3 to the power of 2 edges. So like after that, like the answer is like we choose like k vertices in the graph and like each of like 2 there are like 2 pair of like vertices which is connected and doesn't connect to the other vertices in that chosen vertices.
Is that anything hard or you can do that?
I don't know. I think I can do that one. The problem I think the problem is problem.
It's gonna be hard, probably. The problem you're saying is like maximum disjoint edges. You're picking edges in a graph when those edges share a vertex. It sounds a lot like maximum independent set of edges. In fact, can you reduce maximum independent set to this other problem? Maybe. I'll get back to you on that. But I feel like your version of the problem is likely NP hard. Okay. But we've already done that. We've used to a graph problem, except our graph has very special properties. That's why we can solve it here. But I'll look to see if that problem can be hard afterwards, but I reckon it is. So we have an n to the 6 solution. Now we just want to reduce the time complexity down to something better. N to the 4 will pass. N to the 5 might pass, but n to the 4 will definitely pass. And it's not too bad to get down to that actually. We're going to make 2 optimizations. We're going to reduce the state down to an n cubed state, and we're going to reduce the recurrence down to an order n recurrence at each state. So we're going to drop 2 factors of n from the solution. Let's drop this first factor first. And to do this, we're going to note, well, the first thing I'm going to do is I'm going to remove this first green region from our solution. Why so when we do a recursion, we're never going to consider the first, wrong green region, wrong allowed region. I'm going to draw another diagram. If we have some allowed region here, and we pick some two intersecting wires. Currently, we check all of these allowed regions in here. My first optimization, which will help implementation later, is I'm not going to consider this very first region here. You might say, well, what happens if we were to pick something within this region? Well, my claim, why I'm doing that is I'm just going to say we're going to assume that we picked the earliest choice we could have. Because if we would instead pick something else within this region here, we could have picked that first and then recursed on this latter region. So we're going to assume that the selection we make is the earliest selection we're ever going to make within this allowed region. This will make our implementation a lot nicer, as you'll see later on. Why is it nicer? Well, I said that every region is bound by up to 2 roofs, but my claim is one of these roofs is always the wire that is at the very end of the allowed region. Except in the case of the first region, which is why we are getting rid of it. So consider this allowed region here. These are regions actually upper bounded by only a single wire. This one here. So we only need 1 wire here. Yep. This second region here is bounded by 2 wires, this one and this one. But one of those wires is the very end. So we only have to store min x, max x, and this one extra wire, because we're assuming that whatever the max x y is one of the roof wires. For this third case here, note that we're bounded by this wire here. It happens to be the end coordinate, and so we don't need to store anything here. And finally, the last case, notice that in this case we're bounded by 2 wires, whatever 2 wires define our old region, but because, like by induction, we assume that the end coordinate was one of the 2 wires that bounded this old region, it's going to be one of the 2 wires that bounds this new region as well. So we can actually only store up to one additional wire that forms the roof of the region by assuming that whatever our end coordinate is, that is the second one that defines our roof region. Does that make sense, or have I lost people here? So essentially, reducing our state by removing redundant information. We're saying that the maximum x coordinate happens to always coincide with one of the wires in the roof, or when it doesn't, it's because the end coordinate isn't needed to store the roof. Like if the very end coordinate is the start of a wire, we can just ignore it. Otherwise, whenever the end coordinate of our range is the end of a wire, that wire is one of the up to 2 wires that bounds our region. So we can reduce by a factor of n by only storing minimum x, maximum x, and up to 1 wire that represents the roof of our region. This automatically brings the complexity down to n to the 5, because we have an n cubed state and n squared recurrence. Okay. The second thing I'm going to do to reduce this recurrent from n squared to n is I'm going to make quite a bold assumption. And I'm going to assume that whatever wire we pick to include in our solution precisely starts at coordinate minimum x. Let's say +1. We have what is minimum x? I'm just going to say call it minimum x, minimum x +1. Then move to +1. I'm going to assume that the first wire we pick starts at the very start of our range. So when we pick our 2 wires to potentially link together, I'm making the assumption that the first wire is the wire that starts at min x. Or if there's no wire that starts at min x, it's at the end of a wire, then bad luck, we're not picking anything. In that case, we only have to look over order n choices for the second wire that we pick. Now, how can I make such a bold assumption that we're going to always pick the wire that starts at min x? Well, what if we don't pick this wire? then I can just consider the maximum of what if we do pick the first wire and dp of just increase the minimum x coordinate by 1, keep the maximum x coordinate the same, and keep the roof the same. So if we don't use the first minimum x coordinate as part of our solution, then there's no point including it in our allowed range. We could just decrease our allowed range by 1, because if we're not using this the y that starts at min x, then we might as well not have min x at all. We might as well increment it by 1 because we're not using that part of our range. So our DP looks like, try all order n wires, see if they intersect with min x and the y that starts at min x, and whether those two wires are valid. If so, do our DP. Otherwise, well, do the maximum of that and the answer of DP if we just increment the minimum x coordinate by 1. So this then reduces our complexity down in our recurrence to order n, because we're just considering order n y to be the second wire in the solution. And we're making the and we're doing that making the assumption that we always include the very first wire, because if we don't, we can just increment this by 1 and do the solution like that. That's perhaps a confusing optimization. Have I confused people?
Are you ultimately saying that you don't need to check any other cases? You can just take the first one because any other cases you might want to consider
Is included in this.
are already included.
Yeah. Well, only if we explicitly include this as well.
Okay.
Yeah. So we're saying we're going to consider all cases that don't include the first wire. That's this. And then on top of that, we're going to consider all the cases that do include the first wire. That's a better way of saying it. Yeah. So instead of picking all n squared pairs, we look at all ones that include the very first wire, and then we separately consider all the ones that don't include the first wire by looking at the DP values there. So they somewhat common DP optimization where we note that if some of our choices are included in a different DP state, we just consider that DP state and then only the choices that we have to pick in our current state. Going back, this goes back to what I said earlier about why we excluded the first region here, because by doing that, we can always make the assumption that, because the problem is I couldn't say we always include the last thing, and if we don't, we decrement the last one by 1, because the end of our range stores additional information about what wire bounds our roof. But the lowest x coordinate only stores information about the lowest s coordinate and nothing else. So we're free to increment it, but we're not free to decrement max x because that stores additional information. So that's why we have to do it like that. This makes our DP down from order n to order n to 6. We reduced it, we reduced it again. We now have an order n to the 4 DP. With an order n cubed state and order n recurrence.
Is this our final form?
This is the final form of our solution. I'd be interested to see if you do an n cube. I wouldn't be surprised if you could, but it's not needed to get full. I reckon you could do an n cube. I reckon it'd be really annoying though. Or n cube again. I reckon you could sometimes something to speed it up. But it'll be a pain. More than a pain than it already is. But yes, this is our final form of our solution. And n is up 150 to the power of 4 will pass in the fairly generous 5-second time limit.
560 million.
Yeah. Also, it ends up being a bit better than, because this being less than this divides it by 2. Because not every state is possible, you get like a constant factor improvement. So it ends up being fine. But yes, n to the 5, n to the 4 zone is a bit tight, but it gets a fairly decent constant factor because a lot of states aren't actually reachable. Yeah. So there are more questions.
Anyone have any questions?
This is a very involved solution. I think this is a sort of problem where the general idea behind the solution is okay, but there's so many details behind it that it gets bogged down a lot. The idea is we want to do it dynamic programming on the region that we're allowed to put stuff in. That concept on its own is okay, but quite hazy, I think. But then it's very hard to go, okay, how do we represent the region that we're allowed to put Y's in? What's our recurrence? We pick a Y, what are our new regions? And how do we get it down from polynomial to better polynomial? And that was a lot of messiness, I think.
Seems like people online don't have any questions. Anyone in person? Right. I'm sort of curious if Singying's approach is easier.
What's her approach?
She used a map, and from the way she described it, it didn't sound like she had as much problem. What is, if you're still there, what is your opinion? Was your approach difficult to program?
If my understanding is correct, it's just whether you coordinate compress or not.
Yeah, that's just what one of the.
That's like
Okay.
Like that's whether you know the very start I said reduce coordinates from 1 to up to n. That's what using a map removes.
Okay. So it's just one part. Yep.
Yeah. And so instead of doing +1 here, you're going to do dot lower bound, or the upper bound. Yeah. Does that make it easier? Maybe. I think that's debatable.
I try to avoid maps whenever possible, especially if it's straight, right? But just for coordinate compression, it should be fine.
Yeah. I avoided it because I made use of the fact that the size of the range is small, because I iterated over the entire range. But if you don't do that, then you can use it. But you can do that obviously by iterating through your map. But I tend to avoid coordinate compression because I don't like it. Like it's just annoying to do. But I did it in this case because I thought it would make my life easier.
Yeah, hopefully it will break the points without the map.
Well, I did it with map. I did it with map. You know about a map. Well, I did it with a map at the very start. So you first put it in a map and then you compress it.
Yeah.
And then you only use the map once at the start and then store the compressed values in an array, which increases your lookup time. You can do about a map just by sorting an array instead of doing like a doing an iteration through an array. But using a map will usually make your life easier because maps are easier to manage.
Yeah.
But yes, the question is whether you use the map the whole way through or whether you use the map at the start and throw it away. And that's personal preference. Because it's an analogy for the speed plan problem. The question is, do you coordinate compress there or do you keep everything big and use some other technique? For the coordinate compression, that can be a bit hard, you have to explore the range of coordinate compression, but it's a similar thing.
Using a map is a good idea, and I'm going to use the map from now on.
Yeah, map works as well.
If I can.
Adds a log factor.
Adds a log factor. Comes with the territory.
Yeah. I was looking to see if that problem was empty hives.
It seems like the debugging has also been going well. Any last questions? Any thoughts? It does seem like it's going well. Nam's helping out. The last comment being, "Oh, I see now." It's a good sign. Okay, I think everyone's pretty happy at this point. It's been nice having everyone here. I hope you guys enjoyed the contest. I had no part in that. I'm just here along for the ride. But yeah, okay. All right. I guess I'll end the Zoom call now. Enjoy your evenings, everyone.